Okay, so we last time started talking about word2vec, and we said that word2vec tries to assign 300 dimensional word vectors for each word, so that close by words are close in distance, in Euclidean distance to each other, and using some kind of a linear algebra trick. Where is my carrot? Here's my pen. Using a linear algebra trick, singular value decomposition or PCA, we can reduce this 200 dimensional word into two, which wouldn't be very precise, which would be only approximate. But to visualize it, if I show you that 200 dimensional word in just 2 dimensions, this is what we would get. Okay, so fully unsupervised way without marking anything by hand, and it figures out that these words are close to each other: Tuesday, Thursday, Saturday, Christmas, and the months, year, summer, etc. These are very close by, and these numbers are very close by, etc. Why is this happening? It is happening because remember how we calculated, how we optimize the main objective function. Main objective function says that, okay, if two words happen together, their vectors should be similar to each other. Okay, so I say I saw 5 cars. Okay. When I write such a sentence, all I am saying is that, remember how we calculate the word vectors of cars and 5, cars and saw, cars and I should be similar. That's what we said, right? It's kind of counterintuitive. I mean, why should the I and cars should be similar? Yeah, it should be similar. That's what we are trying to force our system. But we are also forcing most of the time. When I say I saw 5 cars, then I will say I saw 5 bikes or automobiles or those kind of buses and etc. So all kinds of transportation stuff, they all have to show, or they all have to get a similar vector. So they will be similar to each other. So function-wise, they get similar vectors. Syntactically, since because they can be placed in instead of the others, they should have similar vectors. And within the same context, they have similar vectors. So we are achieving many things at the same time, and it turns out that it works very well, and we get such results. I showed you the paper about the unreasonable efficiency of data. Did I show you the paper? Okay, did you read it? Did you read it? No? Read that paper, Unreasonable Efficiency of Data. Okay, actually that paper is based on some other paper, which is a classical paper, Unreasonable Efficiency of Mathematics. Okay, and that guy was talking about how come I can capture the meaning of motion of objects by just this F equals ma. Okay, that guy was kind of in surprised that such a compact equation can capture such a complicated thing, but it turns out that data is doing even better. By using only the data observations without doing any analytical closed form formulas or anything like that, we can do much better than those. And maybe for this one there is a deep theory under it, but for the data there is no theory. There is not much understandable theory behind it, but it somehow works. So we talked about these, and then we talked about these co-occurrences, and people have been working on this for a long time. We said that. Later, they came up with this idea of using co-occurrences, okay, and the skipgram approach under the same framework, and they got these kind of nice results, and GLOW works very well. Other than GLOW, we have many other word representation techniques. Like the best ones are nowadays we are using is maybe this is the most popular one. Not the best one, but the popular one because it is already available. There are lots of trained models available for many languages, and we keep using it. Later, when we talk more about deep learning, transformer systems, we will talk about this more. Okay. Last time I think we stopped at this point. We have lots of vectors, and we think that we did a good job. How are we gonna know that it works good? Okay. So there are two ways of doing it. One is directly evaluating our vectors. The second one is extrinsic. And I think we looked at these stuff. We said that if I take this vector between man and woman like this, I think maybe I shouldn't do it this way. Do it in a continuous. Okay, if I have taken this, if I take this vector and move it on top of king, okay, this should give me around this point there should be queen. Okay, this is called analogy. Okay, if I am successful with this kind of a word vector algebra, then my word vectors are nice. They are working very, very well. Okay, that's what I can do once to evaluate my vector qualities. Okay, to evaluate my vector qualities. The other thing is how am I gonna do this on a data set? Well, I am going to compare it with the human results. I mean, I am going to ask the same question here. I am going to give you strong, stronger, okay, clear, clearer, loud, louder, soft, softer. Then I'm going to give you as a human, dark, and what would you say? Most humans say is darker. And am I getting the same thing with my word vectors? Okay, I'm going to ask that, and it looks like if I train my system on large enough data sets, okay, I can get around 70% accuracy. 70% of the cases I can get good results. They have divided this into two, semantic analogy and syntactic analogy. So what is semantic, what is syntactic? Okay, syntactic is this, strong, stronger, clear, clearer, dark, darker, because syntactically I know how to make superlatives, okay? From stronger to strongest, louder to loudest. You just add est at the end. Okay, that's the syntactic one. Semantic wise is this, okay? Who is the CEO of Chrysler? Okay, who is the CEO of IBM? These are semantic information. I think you cannot capture this kind of information using syntactic rules. So it looks like semantically we are doing better than syntactic version for most of the methods. These are old methods based on singular value decomposition, but continuous bag of words and skipgrams are the ones that we have learned for the word to vec. GLOW is doing a little bit better than those. There are other methods that do much better than GLOW nowadays. So this is one way of evaluating our results. in any area of science or engineering, okay, once you say something, okay, I did this, it works good, you have to show your results experimentally, saying that, okay, I'm comparing my results with other people's results. Or if you say that I am the first one to propose such a system, there are no other people, then in that case you need to show your results based on some kind of a baseline. Maybe a very trivial case of solving your system, which would be very, very bad system. So you should show that you are doing much better than the baseline, etc. Okay, so that's the numbers. Again, these are intrinsic evaluations. And once you do this kind of an experiment, you immediately start doing this kind of a stuff, okay? What kind of a dimension is a good dimension, okay? So I repeat my experiments, this analogy experiment, with different dimension sizes on the same data. It looks like if I keep my dimensions like maybe 20 dimensions, my accuracy is not more than 25%. For 100 dimensions, it is around 60%. For 300 dimensions, it is around, for the semantic case, it is around 80%. If I keep increasing dimensions, that's lots of data, I am not gaining much, right? I am not gaining much. So looking at this picture, it looks like 300-dimensional vectors for this kind of data is good enough, okay? So this is called hyperparameter search, because those are our hyperparameters, okay? Remember what is word2vec? Word2vec is a parameter search problem, and each parameter is an element of our word vectors, okay? We are looking for those word vectors one by one. Those are our parameters. But on top of those parameters, there are hyperparameters, such as how many vectors, how many dimensions should I have for each word, okay, 300 or 200, or how many iterations I should do while I am searching for these vectors, or what is the termination criteria, the threshold value before I stop doing this search, and etc. Okay, these are all hyperparameters, and hyperparameters are not something that you present as your final result. You will say that with this hyperparameter, these are my results, okay? And there is something, okay? Again, the same thing, semantic, syntactic, and overall accuracy. And this one looks at the type of the data and the size of the data. 1 billion tokens, 1.6, okay, 42 billion tokens. It looks like if you increase your data a little bit more, say this is wiki. I think I was asking you about the size of the Wikipedia. It looks like in 2010 it is 1 billion tokens. Now it is 1.6 billion tokens in 2014. So when you increase your data size, all the final accuracies for the semantic, syntactic, and overall, it increases, right? Okay. It is very important to get this kind of a result, because that means what? It means that this method scales very well with the data. You increase the data, your performance increases, okay? Up until these kind of techniques, numerical techniques or machine learning based techniques or database techniques, this was all the way the other. When we increase our data, our results got worse and worse up until this point. Nowadays, whatever data we have, we can do better on that data. That became the norm. That's the good news, okay? Before that, it was just the opposite. More data meant we are going to do worse. Either we cannot train it because it is exponentially expensive to train it, or when you train it, our system does worse. Okay, so these kind of experiments with your data, maybe you can consider them as a hybrid parameter, is something that we do often. Okay, another one is again direct comparison with the human judgment. You ask people; these are very difficult questions actually. You ask people, what is the relationship? How much tiger and cat are related? Give me a number between 1 and 10. Cat and tiger are very, very related, right? Because, I mean, all tigers are cats. So most people said give high numbers, 7.35. And you should expect this, right? What is the relationship between a tiger and tiger? Everybody said 10. It is 10. So what is the relationship between stork and jaguar? It is very, very low. Professor and doctor, you see these there. So, of course, you don't ask this question to a single human. We ask many humans, okay, 10 of them. This is their average. This is their average. Okay, so what am I going to do? I am going to ask the same question to my word vectors. I'm going to ask them, okay, find me a distance between the vector of tiger and cat. Okay, I'm going to normalize the distance between 1 and 10, or 0 and 10, because this is low, right? 0 and 10. And I'm going to see if it is close to this mean. Or sometimes, okay, sometimes it would be, okay, let's say this is my, okay, let's say I ask this question to 100 people, and this is 10, and this is 0, and they are going to tell me something, okay, the difference, the distance between tiger and cat, okay, 10 people said it is 7, some people said this, this, and this. I expect something like this, a normal distribution. So the mean should be around here. It is 7.5. If I ask this question to 100 people, this is something that I would get, a normal distribution. If I ask the same question to my word-to-vec system, if it says it is this, okay, so it is at this point somewhere here, so that means what? I am within the normal variation of people. I mean, you may confuse my result with one of the humans' results, so I am doing as good as humans. You cannot differentiate myself from any of those humans. Numerically, you cannot do that, okay? If I give you 100 people's results and my result, so you're going to have 101 results, and I'm going to ask you, pick the one that is not a human. You can't do that, right? Because I am here, right? I am here. So you cannot differentiate the difference between myself as a computer and the humans. That's what we are trying to do, okay? That's another intrinsic evaluation. And these are the intrinsic evaluation results, okay? How much I am similar to humans in terms of vector distances, okay? Again, let's ignore this one, this one, this one. Continuous bag-offers and SG, skipgrams, are the methods that we saw last week. GLOBE is the combination of this skipgram and the co-occurrence matrices, okay? So if you train your system on 6 billion tokens, billion, very large number, these are the results, and nice. If you train it on 42 billion, then this is what I would get, right? It's very, very good. And somehow if I can get this 100 billion data set, the numbers are all higher. See this one, continuous bag of words, yeah, it is 68, 79, do you see the difference? More the data, better the numbers. It is always like this for these kind of methods, and that's a very, very good news in terms of the final results. We don't know why it works that good. Well, statistics, right? More statistics, better results. but later we are going to see some cases why this should work. We don't understand. That's why that guy says unreasonable efficiency of. Did I tell you about the unreasonable efficiency of RNNs? I did not, I guess, right? So read that paper too. Unreasonable efficiency of mathematics, unreasonable efficiency of data, unreasonable efficiency of RNNs. I think the most unreasonable one is the RNN one. They keep copying it because I mean the structure is so unreasonable efficiency. Oh, I am not connected. Let me try to connect myself. When you come to that one, okay, get connect. That's not a paper actually, it's a demo of or a tutorial of how to use the RNNs. Okay, when you get to that one, it is figuring out some stuff that I mean, even the inventor of that method cannot understand how it is working, why it is working. It's kind of surprising, but that's the way it works. More data, better results. So more data means that your training system training system is efficient enough to handle that data. If you need lots of memory to handle that data, and that memory is not available, then that system is useless. But GLOW and skipgrams are so simple that you can even get this 100 billion tokens nicely. So these are all intrinsic evaluation systems. So we invented these methods just to evaluate our word vectors. That's kind of cheating though. I mean, I invented my evaluation system just to show that my vectors are nice. Some people don't like it. That's why they say that in order to evaluate a new natural language processing model, you need to evaluate it extrinsically, okay? Take that system and evaluate it on a real task, okay? See if that task accuracy is going up or down. And in this case, I am going to use, okay, I am going to use a very well-known natural language processing problem of word sense disambiguation. Okay, remember the ambiguity is one of our main problems, maybe the biggest problem in NLP and many artificial intelligence problems. This is what we are going to do. Take this word pike, okay? Take this word pike. That pike has many meanings in English, okay? It has maybe more than 20 different English. If you look up this word in the Webster Dictionary of English, it's going to give you 20 different meanings, okay? These are some of the meanings. A sharp point or staff, type of elongated fish, a railroad line or system, type of road, the future, okay? So these are some of the meanings of pike. So this word sense disambiguity problem looks for which meaning of this pike I am using in this sentence when I say I am on a pike, okay? I ate some pike food, etc. Which meaning is that meaning that I am trying to tell to you? So this is so important because if I am going to do the machine translation without knowing the exact meaning of the word, I cannot do the translation, okay? I cannot do the translation. So I am going to use the word vectors in such a problem, okay? Versus disambiguity, or I can use this word vectors directly in machine translation, okay? whatever, okay, in a machine translation, I have to represent each word by a vector. Using my words, using my vectors that comes from continuous bag of words, or glow, or skipgram, okay? Which one is doing in terms of translation accuracy, okay? That will give you the final numbers of the system, machine translation of the system. So what is the difference between those two? It is a difference of the word vectors. I think this table is doing the same thing, but this one is doing it for named entity recognition, not for the word sense disambiguation. Named entity recognition is another NLP problem, okay? Named entity recognition is another NLP problem. What does it do? Given a sentence, you just mark the persons, organizations, locations, etc., okay? And if you mark them right, then you are doing good. Am I connected? Okay, here it is. Let me connect to this one. Okay, so with the named entity recognition, whatever the method you are using, you need to represent your words in a way, in a vector way. And depending on which representation I use, these are the final results. Development, taste, and these are the two data sets that I am using. It looks like if you use glow, your final results are the best, okay, with these two data sets. This is not a technique, or this is not a problem that I have invented to validate my vectors. This is an already known method or problem. I am just using my vectors inside this problem solution, and it looks like I can go from 77 to 82. Okay? If you do such a validation, nobody will object to that. Am I connected? Yeah, I am connected. By the way, I think I will keep talking about these NLP problems. Then why don't I show you? Yeah, I got this from Wikipedia some time ago. Okay, these are some NLP problems. Let's go over them because I will keep referring to them. Some of them are very obvious, some of them are not. Automatic summarization. You know, you are given a text, you are supposed to summarize it. There are two main ways of summarizing text, okay? One way, the easier way is this. I have 5 pages of text and I need to summarize it into half a page. I can find the most representative sentences, maybe 3 or 4 sentences, and I can give you those, okay? So summarization becomes just choosing of the text, okay? Choose this sentence or this sentence and this sentence, okay? So this is the easier one. The other one is completely write original sentences out of this 10 pages of human language text, okay? So those are both NLP problems, very famous one. Co-reference resolution, okay? How about this, okay? He entered John's house through the front door, okay? So when you say the front door, you immediately know it is the door of the house, right? So that's called the co-reference resolution. It is not, okay, he entered John's house through the front door. I could have another noun in here, but this noun is a door, and I am saying it after the house. This front door is referencing the house, okay? Good. Discourse analysis is, of course, we talked about this. Remember the Space Odyssey 2000, okay? There was a dialogue between the computer and the captain of the ship. Everybody has to follow some rules, when you talk in society, and we follow those, otherwise our communication wouldn't be natural and people wouldn't talk to us like people. So discourse analysis is this. Okay, so what kind of a discourse I am in? Okay, the nature of the discourse. The way I am talking to you is very different than the way I am talking to the secretary upstairs, right? Or the way you listen to me is very different than the way you listen to the news on the radio or TV. These are very different contexts. Okay, discourse analysis deals with that. Machine translation, we already know about it. Morphological segmentation or analysis is something that is fairly straightforward for some languages like English. Okay, English has fairly simple morphology, but in languages such as Turkish or whatever this language is, okay, agglutinated, okay, languages we call them. Every dictionary entry has thousands of possible word forms. You remember? These are all inflectional suffixes. Kitap, kitaplar, kitapları, kitaplarım, kitaplarıymış, kitaplarıymışçasına. They are all the same inflectional forms of the same word. In English, we don't have such thing. So it becomes very important for languages like Turkish, morphological segmentation. What the meaning of each, what happened? Okay, the meaning of each suffix needs to be segmented and it needs to be disambiguated. Named entity recognition, okay. We say, okay, which item in the text maps to proper names such as people, places, and what type of each such name I should mark, okay. So you might say that it is easy. A proper name, özel isim, it should start with a capital letter, but not all the languages are like that. For example, in German, capitalizes all nouns. I don't remember this, but it says so, okay? Regardless of they refer to names or anything, okay? French and Spanish do not capitalize names that serve as adjectives, okay? So the rules are very different. So by looking at the capitalized words, you are not finding the real people or anything like that. Natural language generation is just the opposite of natural language understanding, okay? You convert information from your knowledge base to natural languages. Understanding is just the opposite. Optical character recognition, nowadays, we don't consider it as a AI problem or natural language processing problem, unless it is written, it is handwritten, because when you start writing in handwriting, okay, ben yazıyorum, I guess, that's what, I don't know. It is difficult to read it. It depends very much on the context. That's why sometimes they call OCR applied on the handwriting is, okay, it is intelligent character recognition. Part of speech tagging is something that we are going to look at later in the semester. It is finding the function of a word within a sentence. This word book, okay, it could be a noun, it could be an adjective, it could be a verb, or it could be something else. It depends on the context. So part of speech tagging is responsible for finding the type of that word in a given sentence. Is the noun, is the verb, is an adjective, etc. Okay. Good. And parsing is finding the grammar of a sentence, actually. When you say, okay, parsing is different than part of speech tagging. In the part of speech tagging, you mark each word by, it's a verb or noun or adjective or adverb and etc. That doesn't still give you the main verb of the whole sentence, okay? The The parsing is one level up. It says that given the grammar of this language, okay, this is the main verb of the whole sentence. This is the main subject of the whole sentence, and etc. So it gives this kind of a meaning to a given sentence. That's called parsing. Question answering, you already know that. I guess we talked about this. For example, if somebody asks you what is the capital of Canada, okay, you are supposed to say, is it Ottawa? Is what? Quebec is a state, I guess. It is not. I guess it is Ottawa, right? Is it? Who said? Yeah, you know. Yeah. Okay. So you are supposed to give me a city name, understand the question, and give a proper name. Relationship extraction. Okay. I read some kind of a text. Okay. After that, I asked this question: who is married to whom? Give me those. Who is the advisor of this professor? Okay. Who are the students of this professor, and etc. Okay. Sentiment analysis is given a text, given as text. You need to give the polarity of the sentiment. This is a positive sentence, negative sentence, neutral sentence. Okay. I like this company very much. This is a positive sentence about that company. Okay. Speech recognition, well, it is not natural language processing exactly, but with the addition of the natural language processing techniques from audio to text, we use lots of natural language processing stuff. Speech segmentation is something to do with this word. Okay, word segmentation is a problem that doesn't exist in Turkish or English, but in some languages like Chinese, Japanese, Thai, okay, they don't have spaces. They write their sentences without any space, one word after the other, okay, and you are supposed to segment those words from each other. Okay, so that's the word segmentation problem that doesn't exist for Turkish or English. And some people say that, okay, why don't we get rid of the spaces between the words? Okay, for Turkish or English, let's try to see if I can segment them out. And it doesn't work very well for English or Turkish as it does for Chinese, because the language developed that way without word boundaries. Word sense disambiguation, I just talked about it. Okay, a word has many meanings, and given a context, what kind of meanings it has, I need to know. So I need to find, we say, this pike here is meant for this meaning. This is for that meaning. Information retrieval is just, this is more than NLP, okay. Databases, we have databases. In a structured databases, we are looking for some data, okay. For example, a SQL query on a database could be considered as an information retrieval thing. Information extraction is more closer to, okay, more closer to, for example, what is the capital city of Canada, uses this information extraction techniques a lot. Okay, so these are some of the sub problems of NLP. Okay, and this named entity recognition, as I talked a little bit before, finding the persons, organizations, dates, locations in a given sentence. Okay, this is a location, this is something, etc. Is called named entity recognition. And if I use my system word vector representations in this named entity recognition system, these are the results that I am getting, and it looks like I am doing very well with the glow. Okay, especially the numbers above 90% is going to be very, very tough to beat. Because in most of the NLP problems or AI problems, especially with AI problems, there is a human ceiling. Okay. Human ceiling effect, okay? If you say that I have solved this problem 100%, nobody will believe you, okay? If you say that I have the perfect machine translation system, nobody will believe you, because what is the perfect machine translation system? Or if you say that I have parsed this sentence perfectly, and I can do this for any English or Turkish sentence, nobody will believe you, okay? Why? Because even the top professors of the linguistics, okay, they cannot agree on some of the sentence parsing results. They say that it should be parsed this way, the others say that it should be parsed this way, or it should be translated this way, or it should be translated that way, and etc. Okay? So there is a human ceiling. That human ceiling means that if you get close to these numbers, 93%, then anything above that can be considered as random variation, okay? Random variation. So you cannot do better than maybe 95%. So what happens if I reached these numbers, 90% numbers? Then that means that you need a new data set that is larger than the previous one. Larger and tougher data set, so that you drop back to 70% accuracy, so you have 30% more to improve. Okay, I already talked about this a little bit, and these are some of the stuff. Oh yeah, should I talk about, maybe I should talk about this a little bit. There is an idea of assigning a different word representation for each meaning of the word. For example, let's take jaguar. Okay. Jaguar is, as I guess, is kind of a musical instrument. What kind of a musical instrument is jaguar? You guys know? Jaguar dictionary, am I connected? Yeah, let's get from dictionary.com. Well, the most common sense of jaguar is this animal, but there are other meanings of jaguar. Let's go to this Webster. Why is it so slow? Yeah, I got it. Definition, did you example, learn, did you know? Where is the other sentence? Okay. Large yellowish, this is the animal jaguar. Am I missing something? Do you guys see where the other meanings of jaguar are? Let's go back and let's try to see from the dictionary.com. Yeah. Okay. No, this is too simple. Okay, this is just giving me the most popular version of it. It looks like jaguar is some kind of a musical instrument. Okay, and we have jaguar. I guess it's some kind of a software too. Do you guys know what jaguar is? Some kind of a Java library maybe. I don't remember it. And what else? And Jaguar is like a car brand name. Jaguar cars. What else? I think that's.
It says Jaguar is a kind of guitar.
What?
It's a kind of guitar.
A guitar, okay. Jaguar guitar. So, can I get that? Like, maybe do it here. Yeah. Is it a brand name? Yeah, okay. So it is so Jaguar is a brand name for a electric guitar, I guess. It's a brand name for a car too. And Jaguar software must be something else. So it doesn't make any sense to give Jaguar a single word vector, right? So if I use this Jaguar in different meanings, then they should have their own vectors. Or bank, right? Okay, this is banking, finance, transaction. These are about the financial banks. And this is a bank. Remember the second meaning of the bank? It is the coastline of a river. Okay. So boundary, canal, gap, plateau, and bank. What other, do I have any other banks? Just two banks. So how do I do this? Okay. Idea is cluster word windows around words. Retain within each word assigned to multiple different classes, bank 1, bank 2, etc. So I am clustering words like that. First, do the word to vector assignment, and then try to see if I can cluster this Jaguar or bank or approach with different clusters. If I can, then mark them as different words. So bank 1 is different than bank 2 now. Okay, so replace all these occurrences of these bank 2s, whichever is closer in terms of vectors, to bank 2 and run the system again. So now you have two vectors for the bank. One is there and one is here. Okay, so that's one idea. Open problem, still we are working on it. Globe or fast text doesn't work very well with different meanings of the words for different sentences, but BERT, it does very well because BERT is designed for that case. Okay, so I guess I am out of time. Let me take some break. After the break, we will continue. But before the break, where is my attendance? Did everybody sign this? Everybody? Okay. Okay, 10 minutes. Lisans mısın, yüksek lisans mı? Attın mı sen? The topic of classifiers will come to our discussions very often. So let's talk about the classification. So what we mean by classification? Classification is defined formally this way. Xi are inputs. For example, our words. Of course, they are vectors. Okay. Or sentences or documents or whatever, okay? So these are our inputs, and yi are labels. So what are the labels? It could be a binary label, yes or no, true or false, or it could be either stuff like part of speech labels, for example, noun, verb, adverb, and etc. So our task is, given this xi, after observing all these data and data, given a new xi, our job is to assign a new label to it. Okay, this is classically is known as classification. Okay, so in our two-dimensional world, okay, two-dimensional world, let's say maybe I can try to make this give this a little bit more meaning. Very classic examples of classification is maybe this. Okay, let's say I'm trying to make a decision on whether if I should buy a house or not by looking at the area of the house, the meter squares, and the price of it. Okay. So if I am in the red region, okay, I am going to buy it. If I am in the green region, I am not going to buy it. Okay, so what did I do? I looked up, I went to sahibindan.com, okay, sahibindan.com. I read all the entries in there, and I say that I would buy this house, I would not buy this one, buy this, but not buy this, etc. So those ones that I mark with the reds are the ones that I want to buy, okay. Those the ones that I mark with the green, okay. Those are the ones that I want to buy. Okay, it looks like if a house is above some certain meter squares, I like to buy it. And if house is large, no matter how expensive it is, I am going to buy it. That's what I am trying to do with this one. I couldn't find a better example here. So this one has each xi here, each xi, x1 here is, it is 100 square meters, and it is, let's say, 500,000 Turkish liras. Okay, maybe, okay, this is my x1. For y1, I will say yes, I will buy it. I will find such pairs x2, y2, x3, y3, etc. Okay, this is my training set. Now I look at a new advertisement from somewhere else. Somebody says that I have 256 meter square house, and it is listed as 5 or 600,000 Turkish lira. Should I buy it? What I'm going to do is I am going to put it in here, like that. Okay, it corresponds to that part. And since I know that it is on this side, on the right side of this line, which nicely separates this plane into two, I am going to buy it. It's just a simple classification method. Okay, I am going to buy it. It's a simple classification method in this case. Okay, it doesn't have to be this simple. And my world is not a two-dimensional world. It is a very, very simplified world. Okay, my world is usually hundreds of dimensional worlds, right? Remember my word vectors? They are 200 dimensional, 300 dimensional. If I try to assign vectors to the sentences, maybe they are even more 100 dimensional. So this is just a simplification, just for the visualization purposes. And it doesn't have to be a line here, okay? This classifier says that yes or no by looking at the line. Maybe it is a more complicated representation. But the idea of classification will not change. It's going to say, okay, I am going to get your data, I am going to run some processing on it, I am going to make a decision at the end, okay? But if I like to use this line, then this is something that we keep using all the time. This is called softmax. We looked at it previously, but let's look at it again. Okay, so you give me your n-dimensional or d-dimensional input vector, okay, and I will give you my answer, probability of it. Okay, so it's going to be like this: probability of true given my vector 0.1, 0.02, 1.21, 7.5, etc. So what is my probability of true? It's going to say, for example, 0.6. If the probability of true is 0.6, then 0.4 will be false. Okay, it's a classification stuff. But how am I going to calculate this 0.6 and 0.4? It says that find vectors for each class. Okay, so remember the vector dot product. I am going to multiply my given vector for that input, multiply it with the input, and take the exponentiation of it, e to the power that one. So it definitely is going to be a positive number. And do the same thing for all the classes, and whichever is producing the largest number will be my decision. Okay, so it could be either 2 classes or many classes. Doesn't matter, I am going to run the same thing. Some people show this as this. Okay, they say that this is a perceptron and these are my inputs. There are n inputs, okay, and this will be my result. Okay, so I am multiplying this xi1 with this w1, xi2 with w2, xi3 with w3, okay, up to xin with wn, and I add them up. Okay, that's the dot product of 2 vectors, right? Xi vector with the w vector. Okay, that will be it. And I feed and I add them up. This will give me a number. And I'm going to do this for all the cases, for all the classes. And since addition of all these classes multiplication will make a number, and this number cannot be larger than that, the result of this division, large division, will be between 0 and 1. Okay, so this is called a softmax classifier, and softmax classifier is composed of making these multiplications like I showed you before. Okay, so we will keep using this over and over again. The important thing is that, how are you going to find these W values? It is the same problem that we have seen in word-to-vector calculations. Again, we are going to use either gradient descent or some other numerical method to find these values. We are going to see them later. Okay, so currently I'm just showing you what we mean by classification, simple classification. And at the end we will have if our word is 2-dimensional word, which is very simple to have, it will be a classification thing like that. I mean, this picture is simple in 2 ways. One is I have only 2 variables, okay, 2 vector dimensions, x1 and x2. I can take 2 things only. That thing is the 2-dimensional word is a very rare. Also, the second thing is trying to classify a 2-dimensional word with a simple line is another simplification. What did we say before? I said that I can generalize this word into n-dimensional word. Instead of having 2 dimensions, we are going to have n dimensions. Right, that's what I can do. And instead of a single line, I will have a hyperplane. It's going to be a plane, but it's a plane of 200 dimensions. I can solve that problem, but it's still going to be a plane. It's a linear thing. If I need, okay, something more complicated like this, so anything to the, let's say, this is my boundary. My boundary is like this. Okay, if I start from this direction, if I walk along this boundary, anything to the left will be positive, anything to the right will be negative. But how am I going to draw this line, boundary? It's not going to be as simple as drawing a line anymore. So my softmax will not work. So what am I going to do? In this case, we are going to use, okay, neural networks. Remember my perceptron? Where is my perceptron? Yeah, this one. So I'm going to use this. It will be another node here, and this will be an output, another one here, an output, and I will connect this one to this one too, and do the same thing here. Okay, and there will be another perceptron here, and it will continue. This one can draw a line, another line, another line. If you combine all of those lines, this can do many complicated stuff on a two-dimensional or n-dimensional space, like this one. Again, we are going to see this picture or this picture over and over again, whatever we are doing. This was just a simple introduction. Okay? Good. Any questions so far? So that's the end of my talk about word representations, and I'm going to go back to discussion about morphology. But before the morphology, we need to talk about finite state machines. That's where we left, I guess. So morphology, finite state machines. Yeah, here it is. Okay, so we talked about those. We talked about, okay, the sheep language. I guess we were around here. Okay, so a sheep language, this finite state automata, it has 5 states, Q20, Q4. There is only one accept state, Q4. And this is my start state, and these are my transition rules. If I am on the state Q0, if I observe a B, then I do a transition to Q1. Then if I observe an A, then transition to Q, then it goes like that. Okay? And at the end, if I am on Q4, then I accept the string. So if somebody gives me B, A, an exclamation mark, then this is an acceptable string for this language. Okay, very simple language, but I can say, using this formalism, I can say this is acceptable. Okay, so I think this is what we covered previously. But then we have this kind of finite state machines too. Okay, this one, and let me show you two at the same time. Both of them accept exactly the same string set, and they reject exactly the same string set. But one of them is a deterministic finite state machine. The other one is non-deterministic. Can anybody tell me what do I mean by this is deterministic and this is non-deterministic? Power-wise, they are same power. They represent the same language. Okay, whatever this one can accept, this will accept. Whatever this one rejects, this will reject. So they are representing exactly the same thing, but this is a deterministic one and this is non-deterministic one.
There's 2 options for A at the bottom one.
At state Q2, if I observe an A, I can go to Q3 or Q2, right? I don't have such a thing for this representation. Okay, it is always deterministic where we go. Okay, so how do I know where to go if I observe a new A in this case? Well, you have to test all the cases. Okay, you have to test all the cases. If I go this way, and if I go this way and this way, can I accept the string? No, then maybe I should go the other way. Okay. So which one would you prefer, the deterministic one or the non-deterministic one? If I am the programmer, of course deterministic one is the better, right? Because it is so straightforward. I have 5 states. I know how to transition from one state to another one. There is only a single option. Okay, you either, if I observe an A, I go to Q3. If I observe an exclamation mark here, I say fail. If I observe a B here, I say fail, and that's it. For this one, if I observe an A, it could be either this one or that one. So I have to test both of those paths. So this is difficult, more difficult to implement, right? But the thing is that, but on top of it, what did I say? This is not any more powerful than this representation. Whatever this can represent, I can represent with this one or vice versa. Okay? But sometimes we will prefer this representation for us only, for the humans only, because with this one I can write some machines even with a shorter notation, shorter lines of description than the deterministic one. We are going to see them later. So more formally, a finite state automata consists of these 5 things: set of states, 5 of them from Q0 to Q4, 0, 1, 2, 3, 4, and then finite alphabet, okay, A, B, and exclamation mark, and that's it. That's my alphabet, okay, and start state is Q0, okay. A set of except final states is Q4 in this case. So question for you, why do I have a single start state, but for the except states or the final states, I have a set? It says that start state has to be a single thing, okay, single state, but except final state is a set. Can anybody tell me? Well, in this case, it looks like start state and this is the final state. There is only one final state, and I could have more than one final state. Start state has to be only one, okay, one state. That's how they defined it. Can anybody tell me why they have chosen it this way? Yes?
Is it like classification? For example, for input, we can have more than one output, and we usually take the maximum one. And here we...
Yeah, that might be one of the reasons. I mean, I can accept the string with a Q4, but sometimes I can accept that string with Q5. I am both accepting them, but the way I accept them is different, right? It might be it. So that's how it is defined, and we are going to see examples of it later. Okay, and finally, I have a transition function. This transition function says that, okay, from Q cross sigma to Q, give me a state and an input, then I'm going to give you a new state. Okay, and let's look at this finite state machine. It's a very simple thing. It says that I am going to accept strings of English money amounts between $0 to $100. Okay, whatever you give me, if I can accept it, then it will be a acceptable thing. So if you say $40, 39 cents, $40.39, would you accept the string as that's American dollar value? Well, I am going to look at this. Where is 40? 40, so from Q0, 40 to Q2, okay, dollars, then Q4. So from Q0 to Q2, then Q4, and 39, and $40. Where is 30? Then 30, yeah, this is 30, yeah. 39 cents. So it's going to be from Q0 to Q2, then Q4, then Q5, Q6, after 9 cents, Q7. My inputs are done. I finished my inputs, and I am at Q7, accept state. So I accepted this string as a valid US dollar value of between 0 to 100. Okay, so there are two final states. One is Q4, the other one is Q7. So if somebody says $40, that's fine. $40, right? $40 or $16. That's it. It works. Okay, just a very simple finite state machine. You might say that, I mean, what are we doing here? I mean, these are simple kid stuff. But as I said before, remember the paper I showed you about Turkish morphology. I mean, a language like Turkish, as complicated as Turkish, the morphology can be represented using this kind of a finite state machine, and it works. I am not talking about disambiguation, okay? I cannot tell you which morphological analysis of a given word is the correct one. I am going to give you all different types of morphological analysis of a given word using finite state machines. Okay, good. By the way, this is how you represent. Remember this one? Remember this transition function? This is how we represent it in a simple way. Transition function. If you give me, okay, while I am at 0, Q0, okay, if you give me a B, I will be at state 1, okay? While I am at state 1, if you give me an A, I am at state 2. If I am at state 2, if you give me an A, you will be either in 2 or 3. So what does that mean? For a non-deterministic finite state machine, you can have more than one state name or number in a given box. For a deterministic one, you can have at most one state name. So this is a non-deterministic one. Okay? So this is a transition function represented by a matrix. Another representation is this, of course. Okay? So the recognition is simply running your string through the finite state machine, either this representation or this representation. If you end up on a final state, then you recognize it. Otherwise, you reject it. Okay, you reject it. Recognition is simply this. Okay, so usually the computer theory of computer science people, they try to represent whatever they have in Turing notation so that you will say that this is something computable or there is no way to compute this, and etc. Okay, this is how we see it. We say that our input is written on a tape, like a regular Turing machine, right? And we read this tape, and we update our states. And if at the end I am at the correct state, final state, then I recognize it. That's how the Turing's notation is going to work on this one. Okay, so this is the algorithm that we run. This one says that, okay, you run this algorithm, whatever your inputs are or whatever your machine is. So derecognize, this is deterministic recognize. It takes a tape. Tape is this is the input. Okay, and it takes a machine, finite state machine. Remember, this is the finite state machine. This is the number of states. This is the transition table or function. Start state, final state. Sorry, this is transition table, and this is the alphabet. States, alphabet, transition table, start state, final state set. And this is my machine, and I give this machine as an input to this derecognize. Okay? If we look at this derecognize, deterministic recognize, see there is a loop here. This loop says that end of input has been reached. Reading the tape one by one. Did I come to the end of the tape? No or yes. Okay. If I am at the end of the tape, then the current state I am in is then accept state, then I am returning an accept. So this is the happy ending. I am finished with my input tape, and my final, the state I am at is an accept state, and that's it. Otherwise, return or reject. See, this function returns either, let's say, a Boolean, either accept or reject, true or false. Okay, let's look at this one. What does that mean? So there is only one condition for accept. That condition is these two if statements. I am finished with the whole input. The second is I am at an accept state. For reject, there are two cases. One is this. I am at the end of the tape. My current state is not a accept state. How about this one? What is this? What is this reject? So it looks like there are two ways to reject a string. One is I read everything. Okay, I read everything, but I am not a accept state, final state. The second one is
Empty cell.
What do you mean?
Transition table. In transition table, we are going to an empty cell, so we reject.
Yeah, it is like this. I am at this state 3, and I got an A as an input. If you are at this state and if you got an A as an input, there is nowhere to transition, so I am going to reject it. Okay, that's reject. So the nice thing about this algorithm is, it is the same algorithm whatever your machine is, whatever your input is. Very simple algorithm, and you keep running this algorithm for any input that you might have. Okay, that's the deterministic recognize. For the non-deterministic recognize, okay, non-deterministic recognize, these parts will be the same. No, well, I mean, remember this one? For the non-deterministic case, my current state cannot be deterministically a single state. I have to branch in here, okay? And my reject will be different. Okay, let's see this non-deterministic finite state machine in an example, and we are going to do it as state space search. You guys remember state space search? I think I gave you this example. For example, what did I say? From intention to execution, I can do three things, right? Either I can delete I, in that case, it's going to be this, or I can insert an E and 10, or I can replace I with an E and 10. And if I continue doing this, okay, in this space search, at the end, somewhere in the middle maybe, I am going to find the execution from intention to execution, and that will be my shortest path to the solution. It's a nice algorithm, compact algorithm, but it was too expensive. Remember that? So I am going to apply the same idea in here, state space search. This is what I am going to do. Okay. This is what I am going to do. I am going to show you the result, and I will come back. Okay. This is my input, and these are my final state machine stuff. Initial state and the final state, etc. Okay. So at the beginning, I am at this position. I am reading this, okay, Q0. When you read Q0 with a B, I definitely go to this case, my tape. This is B, this is A, and Q0. A, and that's it. Now I am pointing to this one, right? Okay, let's continue. Like I said before. Now I am doing this state space search, but I have only one way to go. Okay, that's the place. I cannot branch more than once. Now in the second case, I am at Q1, and I am reading another A. Again, it will be like this. So it's like a tree, but it started with a single node, another single node, another single node. This time I am at Q2, and I'm going to read an A. I have two possibilities, okay? I can stay at Q2 or I can go to Q3. This guy says that, okay, I am going to go to Q3. Okay, I went to Q3, okay, and I am reading an A, Q3 and A, it won't go, okay? According to the algorithm of derecognize, I have to reject this, right? But this is not a derecognize algorithm anymore. This is ND-recognize. With the ND-recognize, if your transition table is empty at that location, you don't automatically reject it. You go back, you backtrack, and you try the other possibilities. So what am I going to do? I will go back, okay? I will continue from the other direction, saying that, okay, maybe instead of going Q2, let me stay at Q2, okay? That's what I am going to do. This one is a okay, bad thing, so I will come back. I will go to Q2, and again, I have two possibilities with the Q2, okay? I can go to Q3, I can stay at Q2, okay? Which one should we do maybe? I think I should do Q3 because I see that it's going to end later. But again, there is a branching here. And I will do that, okay, go to Q3, and I will accept it. I didn't check this other path. Since I accepted this string. But before accepting this, maybe I should go to other path and see if I can accept it in any other way. Because with the non-deterministic finite state automata, okay, it is important to check all the paths. Maybe there is more than one way of accepting a string. That's important too. Okay. Maybe there is more than one way of accepting the string. So that's what we say. That's what we mean by. Okay. That's what we mean by how we accept a string by non-deterministic finite state automata. Okay, so unambiguous regular languages are okay, but ambiguous ones are okay too. I can handle it with no problem. Of course, it will be more expensive, but I can do it. Again, the interesting thing is, okay, these two, okay, represent exactly the same thing. If somebody gives you this finite state automata, non-deterministic finite state automata, there is a way to convert this to a deterministic finite state automata, always. So there is always a corresponding deterministic finite state automata. It doesn't have to be the same size. The number of states are usually exponentially larger, but there is a deterministic corresponding one, and there is an algorithm to find it. So this is not more powerful than this one. That's the important thing. Okay, are there any questions so far? Okay, good. Then remember, just to keep you motivated, let me go to this. Where is my? I think I uploaded it to our. Yeah, here. Okay, here it is. This whole paper. Okay. By the way, read this paper before coming to the class next week. Okay. This whole paper is about these kind of finite state automatas. Okay. We are going to combine them later, but in our case, okay, we will keep, okay, this guy says that I am going to make in my alphabet are Turkish alphabet, okay, I am going to call them VS, I, okay, these are the vowels, 1, 2, 3, 4, 5, 6, okay, these are the surface vowels under certain cases. This is, okay, that's it. These are the lexical vowels. H means, where is my H? H means, I think it is I, both of them. And some of them are really different. And I define those. And if I go one level up, okay, these are the H, right? H is this. V's, I forgot what the V's are. Yeah. I think H is I. Masam. Kitabım. Masam, kitabım. And sometimes H just goes away, this H. And if I, okay, as you see at the end, there is a start state, and these are the transitions, and these are the inputs, okay? And these are the ends, these are the final states, acceptable, okay? To come from a nominal root, a noun root, to plural, then to go to processive, then just with this suffix, then I end it. So this is a accusative noun, okay? Accusative noun is hali, ismin. Dative is hali, right? So these are when you say, if you follow this route, you are going to end up in the accusative noun. These are the accusative noun. These are the adverbs, okay? For the whole language, attitude adverb, nominal verb, etc. So this is the finite state automata. Of course, it's a non-deterministic finite state automata for the Turkish morphology, okay? Nominal morphopatics. And I guess these are these are only for the nouns. By the way, when you got into that verbal root, there is another finite state automata for the verbal root, okay? And you will run that one. Yeah, verbal root is here. And if you follow that one, there is one and another and another and in here. Verbal stem is, with a verbal stem you come from here. Which one? Let's look at this one. From verbal stem to, see this one, just when you say kosh with no suffix, imperative at no suffix, zero means I did not add anything, and add, so it's an imperative word. So what is this? How about this? Can you guess what this is? Kosh, 0, 0, and. How about kosh? How about this one? Sun, right? Yeah. H can represent I, U, and etc. It was defined there. How about this one? This is koşsunlar. Koşunuz. It is imperative again, right? So, I mean, what I am showing you is not kids stuff. This, I mean, what did the slide say previously? Morphological segmentation. I mean, morphological segmentation is something easy for English, but for languages like as complicated as Turkish, okay, it is not that easy to, okay. For English, you don't have to do the morphological analysis much because, I mean, when you take this word open, it is either verb open, okay? Open, opens, open, then opening, that's it, right? So that's it. But when you are in Turkish, when you talk about open, açmak, open, okay, there are many inflectional forms of it. You cannot represent that word by a few extra words like this one, okay? That's why it is very difficult to assign word vectors to Turkish words because there is not a single open or opens, etc. In English, it is easy. One vector for this one, another one, another one, another one. But for the Turkish word open, there are 5,000 different forms of it. And I am going to repeat this. And if I try to assign vectors for each of those, it will be a big trouble. So this is not a good idea. For such a language, again, for such a language, whatever I am using as a morphological analysis method, I can use the same method for Turkish too. And this is the kind of the proof that it works. Okay? Simply being very careful and doing it one by one, all the rules one by one. This is what we are going to do later, and this is exactly what we are going to see here. Okay, we will write many finite state automatas, okay, for different rules, and there is an automatic way of combining all these finite state automatas into a single automata, and that will be done automatically. So I will deal with only these n orthogonal rules, and they will come together, and we'll make a morphological analysis method. Okay, so go back, and that's what we're doing. Any questions so far? And always keep in mind that this Çöltekin's, okay, Çöltekin Turkish morphology. Am I connected? Why am I not connected? I am not connected because I did not do that. Okay, let's keep that in mind. That paper is more than just the Turkish morphology. It talks about the Turkish sounds too. Remember this at the beginning says these are the Turkish sounds we produce, we use. Okay, so these are the consonants. These are the consonants, okay, that we use in Turkish, and these are classified as, for example, this dental T and voice the stop, and these are where are our constants? Yeah, these are the vowels, okay, and I'm going to show you the classification why we classified it this way. For that, you are going to go to IPA chart. There is an IPAchart.com. Go there. It will tell you all kinds of sounds that a human vocal tract can produce, human mouth can produce. Okay, let's look at some of them. For example, this one. Someone say that these are your lips, closed lip and open lip. When you say ah, okay, you keep your mouth open and your lower part of your tongue is low, okay? This is how you produce that sound. So I think this is more closer to Turkish ah. How about this one? I guess either this. I think this is our ah. Sometimes we use this one and sometimes we use this one. Yeah. Sometimes we use this one. So these are all classified that way, and these are the consonants. And this one is, did I click on it? How come it's not? Oh, my internet is gone again. Is it because am I connected now? Do it again. Very slow, but it works. Anyway, maybe I should stop here. And what I'm trying to say is that we have all that information, okay, this front, okay, where your tongue should be the front of your tongue and back side of your tongue. It should be high or low. And these are the lips, okay. For this one, for the A, the front and the high part should be low and your mouth should be open. For these, okay, that's only the voices that we are using. Out of all these voices, okay, we are using only a subset of it. Of course, it is the number of voices that we are using is more than the number of letters that we have. And you can find them in here, right? Yes. I mean, this paper is more than just a morphology paper. It talks about the phonetics of the language too. Okay. So let's take some break. After the break, we will continue. And I will try to understand why I cannot connect to the internet.
Hocam bir şey sorabilir miyim?
Evet.
Yanlış mı anladım onu anlamadım da deterministik ve non-deterministik olana aslında aynı mı dediniz?
Non-deterministic daha kuvvetli değil. Non-deterministic'in yapabileceği her şeyi deterministik de yaparım. Ama farklı bir tane final state otomata yapmam lazım onun için.
Evet, çünkü yani sonuçta ünlem yaparsam non-deterministikte geçiş yapamam. Q3'ten Q4'e.
Onun ikisi birbirine denkken ikisini gösterdiğim iki tane final state otomata vardı ya, deterministik ve non-deterministik. Birbirine denk onlar. Yani birisinin accept dediğini öbürü de accept diyor, reject dediğini öbürü de reject diyor.
Ama ünlem gelirse deterministik olan kabul ediyor ama diğeri kabul etmiyor.
Non-deterministikte sonuna kadar gitmen lazım. Sen şey diyemezsin orada. Nerede non-deterministik? Burada, tamam mı? A'yı aldım. Ondan sonra bir tane daha A geliyordu. Bak ünlem geldi. Bunu reject diyemezsin. Çünkü diğer yolu denemedim. Diğer yolu deneyeceksin.
Tamam.
Yani bununkisi biraz daha zor. Tüm yolları denedikten sonra hiçbiri Q4'e gelmiyorsa o zaman
Tamam.
diyeceksin ki reject.
Tamam, anladım.
Reject etmek için bayağı bir işim var. Accept etmek için de bayağı işim var. Çünkü olabilecek tüm accept'leri denemeye çalışıyorsun.
Evet, sonuçta bir tane olmayacak, birden fazla olacak normalde.
Hani masalı verildiği zaman masalı acaba iyilik ekili masalı mı yoksa içinde masa olan bir yer mi? Anladın mı? Yani iki tane accept'i var onun. İkisini de bulup çıkarman lazım. O nedenle non-deterministikleri daha çok seviyoruz. Bizim için ifade etmesi daha kolay olur.
Tamam, anladım hocam. Teşekkür ederim.
İsterseniz cana sorun. Yani çant engrolink de atıyorsunuz. Herhalde değil mi? Çant engrolink. Arada Nginx var ama herhalde. Evet. Var mı? Siz ara mı? Ha. O zaman kim diyelim önce birleştirip sonra atılıyor. Onun için yani sen memory kullanabilir diye ben öyle anladım bence. Tam gelirken hem geliyor hem üstüne memory mi patlıyor? Yollayamadan o framework şey yapmaması lazım yani. Parça parça geliyor diyorsun. Yani okuyan tarafla şey ayrı demek. Basma tarafı ayrı. Arkada hızlı hızlı okuyabilip sana atma kısmını daha yavaş yapabiliyor yani. Ya sana tabii ki anlatacağım. Okuya geldiği gibi okuyorduk, noktaları koyuyorduk işte. Sanki böyle bir şey daha önce konuşmuştuk ama işte ben hatırlayamadım ya. Bilmiyorum. Ama böyle bir şey yaşayan var mı? Hangi hatırlamıyorum ya. İş. Ben de ekledim de. Yani bir deniz falan var. Deniz okuyabiliriz. Varsa ekleriz. Ama yok yani menülere koymamız lazım bizim işte. En fazla 10 megabayt aklınızda olabilecek bir şey varsa işte bilmek de var. Bazı konfigürasyonlar oluyor. İhbarları var da. eskiden Trotnik vardı. Trotnik varken herkes bunu yaşardı yani. Bilmiyorum ya. Bir şey değil yani. Sesli söylüyorum. Örneğin fena değil. Kolaylıkla yavaş yavaş. Diğer taraftan da böyle. Özledim ya. Planlanması falan lazım artık. Güzel bir yazı böyle. Yıl sonu sınavlarına falan geçiyoruz. Öyle bir şey olması gerekiyor ya. Yani zorunluluğumuzda. Ama bir ara Erdem bir şeyler saplatıyordu işte böyle. Bazı durumlarda patlıyordu sonra nasıl altı oldu bitiyor. Belki olurdu işte. Çok böyle çok fazla yüklesi böyle patlıyordu. Benim şansım kaçtı da işin olacağı yüklenirsin.
Ekran ne kanka böyle bakayım. Seninkinin aynı. Aralık. Nasıl istersen abi. Nasıl çıkacak orada ama? Yeni ustam oraya nasıl geçecek? Ona göre çıkıyor.
Okay, I had a small question during the break. People are asking me if I go to this state A and there is no A coming again, and there is no question mark, should I be rejecting it? No, the answer is of course no. As I said before, you should test all the paths, all the possible paths of a non-deterministic machine to reject an input string. So this machine is more difficult to execute because you need to explore all the possibilities. But still, I mean, it is not more powerful than a deterministic finite state automata. We talked about that, and okay. State space search, we talked about it, and I showed you an example. And all the machines that we have so far, they can be used as generative formalisms. They can generate strings too. On top of recognition task, they can be used to generate strings, and their generation property is nice. They can generate all and only the string in the language. Whatever can be recognized, they can be generated. They don't over-generate, okay? If they generate something, it is acceptable, okay? That's something nice, and we will be using it. And the same thing again here, okay? So these two are non-deterministic, right? They are not deterministic. These are all non-deterministic, both of them, but they are equivalent. They accept exactly the same language. They reject exactly the same string set. and they are equivalent to each other, whatever you use. And there is a nice thing. The nice thing is there is a non-deterministic finite state automata that will do exactly the same thing, and we'll talk about these later. Okay, so let's go back to this non-determinism thing. This is non-deterministic. Why? I have two ways to go if I observe an A here. I have two ways to go. No, it's a, I did, well, this is not non-deterministic, right? This is deterministic, right? Yeah, sorry. So this is deterministic. This is non-deterministic. They are exactly the same, okay? This is much easier to run than this one. This one has it has only one way to, the state space search tree for this one is going to be start, then this, then this, then this, then this. If at the end I am at the Q4 state, then I am done. This one is different. I can branch, okay? Sometimes in two places, sometimes one place. So this one is more complicated, but they are equally powerful, okay? So this is one way to do non-determinism. Given A, I can stay at Q2, or I can go to Q3, or we can have these epsilon states, epsilon inputs, okay? Epsilon transitions. To go to Q1 from Q0, I need a B. To go to Q2 from Q1, I need an A. To go to Q3 from Q2, I need an A. To go to, okay, to go to Q4 from Q3, I need an epsilon. But to go to from Q3 to Q2, I don't need anything, okay? I can jump directly from Q3 to Q2, okay? Without reading anything on my tape, okay, I can jump from Q3 to Q2. That's called the epsilon transition, okay? And these transitions are used very often in non-deterministic finite state automata, okay? Without reading anything, I just jump from one state to another one. This is very powerful. Why? Because let's talk about this. Let's say I have a finite state machine 1 and finite state machine 2. Let's say this one recognizes a set of words. This one recognizes another set of words. Then if I like to make a new finite state machine that can recognize both of these words, then I can do this. Okay, this is my Q0 state, epsilon transition, and this is Q10 state, and this is a final state, epsilon transition. So I have a new finite state machine now that can recognize or generate both of these finite state machine words, okay? Very powerful. Again, this whole thing is a non-deterministic finite state automata, and it can be implemented, can be converted to a deterministic finite state automata, and in that case, can be implemented very efficiently. Okay, so that's why we like this epsilon transitions a lot. Okay, good. Again, I kept saying this over and over again, maybe 10 times. Non-deterministic machines can be converted to deterministic ones with a fairly simple construction. By fairly simple, I mean fairly simple set of rules. Okay, so there is no power difference between those. I cannot say that one of them is more powerful than the others. Okay, non-deterministic recognition, we talked about this. We can do it two ways. Using this algorithm, convert a non-deterministic finite state automata to a deterministic one and run it with the derecognize, the algorithm that we have seen, or run it directly using the state space search that we have seen before. Okay? Using the search, remember what we did, okay? Remember what we did? This one. We can do it that way. Usually we prefer doing it with the converted to a deterministic system and run the derecognize accordingly. Okay. So we talk about this. So why bother? I mean, if non-deterministic finite state automata is not any more powerful than deterministic one, why bother? The answer is, for us it is very easy. Okay, for us it is very easy to remember what I did here. Remember what I showed you. Where did I put it? Okay. For us it is very easy to represent two finite state machines like this and put them together. Okay? It is easy to show, it is easy to understand, and it is easy to debug, right? If there is a problem with one of my finite state machines, I only debug that one, not the others. Okay? So non-deterministic ones are easy to deal with for us humans. That's why we prefer them for humans. More natural, understandable solutions. Okay? Let's look at this one. Okay, the one that I showed you. Finite state automata 1, finite state automata 2. This is sheep language. It only recognizes the sheep language. This is chicken language. It only recognizes the chicken language. This whole finite state automata, and the new one, non-deterministic one, can recognize both sheep language and the chicken language. Okay, both of them. Concatenation is, after each sheep word there is a chicken word, then I can do this. This is the concatenation. Okay? This is the concatenation. This is kind of union, right? This is concatenation. Negation is this. Okay, it's very interesting. I like to have a finite state machine that will recognize all the words rejected by this other machine. Okay? So whatever this sheep language finite state automata rejects, I will accept them. So how am I going to do that? Negation. Construct the machine M2 to accept all the strings not accepted by M1 and reject all the strings accepted by M1. Invert all the accept and not accept states is M1. That's it. As simple as this. Okay? That's it. So this is what I am going to do. If I go to my sheep language, okay, I am going to take the negation of it now. So it is exactly the same thing. So Q0 will be final state. Q0 will be final. This will be final. Final, final, and this one is not a final. This is a regular Q4, okay? So that will be the negation of it. Okay, this will take a B, single B. Okay, it is accepted, right? And BA will be accepted, right? BAA will be accepted, but it should not be accepted. It is accepted. And BAA exclamation mark will not be accepted because this is not a final state. That's the whole thing. That's the negation. So why am I after this kind of a weird stuff? Okay, why am I trying to do this negation thing? It is because this. Remember the Morgan laws? The Morgan laws? What does it say? A union B is equal to, I can do A union B, right? Union, this one and this one. Or maybe this one. Let's do this. A intersection with B. I am going to write a finite state machine that will accept only the words that will be accepted by both A and B. So how am I going to do this? Negation of A union negation of B, right? I know how to do the union. I know how to do the negation of both. And I know how to negation of the whole state. So I can write something, a finite state machine, that will accept the common words of both A and B and nothing else. Okay? So with this negation, I can do that. So that's the intersection. That's the intersection. Good? So
To make
that
it simpler with few steps, few states.
no. It is just for us humans by saying that if I have a finite state machine for Turkish, and if I have a finite state machine for example, for Ottoman language, okay, I like to have a finite state machine that will accept the common words, okay? So it's just a simple Turkish sentence. I can explain it using this notation in a very powerful way. I don't have to think about how it is implemented, how it is. When you do that kind of stuff, you are going to explore the number of states. Because remember how I take the union? The union requires you to introduce some epsilon transitions. Epsilon transition means that you are definitely non-deterministic. When you do the non-deterministic, to convert it to a deterministic one, you will have many more number of states. So you are definitely making your overall finite state machine more complicated, more number of states, more transitions, and etc. But for us humans, it is easy to talk about these. It is a simple intersection of these finite state machines, or the union of them, or concatenation of them. Okay? I mean, with the non-deterministic ones, it is possible to have this kind of notation. That's why, what did we say? It is powerful, yeah. More natural, understandable solutions for humans. It's like writing object-oriented code. Sometimes with a polymorphic code, you will say, okay, for all the objects, O.print. That's all I write. There are many things happening under the hood. Polymorphism is happening, and functions are automatically selected and they are run. It is very easy for me to think about it, but under the hood, if you think about the assembly, it is very complicated. This one is the same thing too. I mean, for us humans, it is easy. For the machine, non-deterministic one, deterministic one especially, it is more complicated. Good. So this was just an introduction for the morphology. Let's start doing the real morphology now. Can I open it? Okay, finite state machines, and let me go to the, I believe I uploaded all these slides, including this one, morphology. We'll talk about the English morphology, and of course we will be referring to Turkish morphology a lot too, and we will use finite state machines. The transducers are kind of finite state machines, and morphology means it is the study of the words. Okay, they are very useful in dealing with the lexicon, set of words. Lexicon, that's what it means. Okay. Let's start talking about, this is a common thing for all the languages, okay? Morphology is the study of the ways that can be built up from smaller meaningful units. They are called morphemes. Morphemes are basically stems and affixes, kökler ve ekler. Affix means it's an ek. It could be a prefix or suffix, ön ek, son ek, okay? Usually in Turkish we have suffixes, not prefixes but suffixes. Stems are the roots, kökler, okay? So we keep adding suffixes or add affixes to the end of the words to make other new words or to get inflectional forms of the words. Türetme ekleri, yapım ekleri vardır ya. So affixes are used for both of them. Okay, so in Turkish we have both inflectional, çekim ekleri, and derivational, türetme ekleri. Okay, and as you know, both of them are complicated. Both of them are involved. In English, okay, remember for the book, I have only, especially for the inflectional one, for the book I have book, books, booked, booking, booked, and that's it. I get 4 or 5 forms. But in Turkish, I can say kitapları, kitaplara, kitaplarda, kitaplardan, kitaplarım, kitapların, etc. Kitapmış, kitapta, etc. So their roots are the same. I am not changing the meaning of the word kitap. Kitap is the same. So it is inflectional. This is çekim ekleri. Okay? So it is complicated. Still, we are going to use the same method to analyze Turkish. Analyze Turkish for inflectional morphology. Okay. Word classes. For now, we are not going to talk much about word classes. There are many word classes. Sometimes for English there are more than 90 classes of words for some of the classification systems. But for now, we will be dealing with the word classes like noun and verb. Fiil ve isim. Okay? Fiil, the verbs and nouns. Okay? Nouns and verbs. And later in chapter number 5, there will be lots of word types, and we will talk about them. Okay? Inflectional morphology, çekim morfolojisi. Okay? It concerns with the combination of stems and affixes. The resulting word has almost the same meaning. Okay, the meaning did not change. Kitap and kitabı and kitabım and kitapları, they have the same stem and their meaning is the same. And why do we have the inflectional morphology? It serves a grammatic and semantic purpose. Okay. When you say kitabı okudum, kitapları okudum, kitaplarımı okudum, okay? It serves a syntactic, grammatical purpose, also semantic purpose too. When you say kitaplarımı okudum, you immediately know that those are my books, okay? And for the grammatical case, for some places, when you say, for example, in English, when you say books are read, okay, you don't say book are read, okay, it has to be books. Otherwise, grammatically, it is not a correct sentence. It is different from the original word-wise, but it is transparently related to the original. It is about book. Okay, nouns and verbs in English, same. But in our case, in Turkish, both nouns and verbs are problematic in terms of inflections. Not problematic, but I call them complex. Okay. For English, for the inflectional morphology, for the nouns, all I have is the plural case, right? You say book and books, and that's it. I don't have any inflectional forms other than plural ones. Okay. Or when I say, okay, his books, or it is the books cover, yeah. Book. Okay, books or books cover. Either possessive, iyilik eki, or çoğul eki, plural. That's it. The same as. Verbs, inflectional forms. Okay, slightly more complex, but it is not that difficult, okay? Remember, book can function as both noun and verb. When it is in verb form, again, I can say books, I can say booking, and I can say booked, and that's it. when they say verbs are slightly more complex, it doesn't mean that it is as complicated as Turkish. Okay? Of course, we have problems with the regular and irregular nouns. Okay? For example, for mouse, we don't say mouses, we say mice. Okay? For the goose, we don't say gooses, we say geese. Okay? Ox and oxen, etc. The same thing with the verbs. We don't say go. We don't say go ahead. We say went. We don't say flied. We say flew. Okay. So some irregularities, it happens. They are not difficult to handle, but it is there. Okay. So regular versus irregulars. This is the simple stuff they teach you when you start learning English. Easy to handle by a finite state automata. Let me show you one example. Okay. Okay. A few examples about the. Yeah. This is a simple rule for the plural finite state automata. For the regular nouns, okay, any noun, a regular noun, I can accept it. If I add an s at the end of a regular noun, I can accept it. Okay? Or irregular singular noun, I can accept. Irregular plural noun, I can accept. And if I list all of these irregularities, irregular nouns, large ones, but still it's a simple finite state automata. Okay? To make a noun plural, okay, our Turkish finite state automata is not difficult either. It's just you add a lar or ler at the end. That's it. Okay? So I can represent regulars and irregulars that way. Okay. Inflectional morphology and irregularities. I will write separate rules for each irregular ones. Derivational morphology. In English, it is more difficult than the inflectional morphology. Why? Because remember, the derivational morphology changes the main meaning of the root word. Okay, it is not the same word anymore. When you say, for example, a few examples. Computerize, computerization. Computerize is a verb. Computerization is the noun version of it, right? So appoint is a verb. Appointee is a noun. Kill is a verb. Killer is a noun, and etc. So they all change their names. The computerize and computerization have different meanings. Kill and killer have different meanings, and their forms are different. Adjective from verbs to adjective, etc. Right? So these are the derivational examples. That's why derivational morphology in English is more difficult. Okay, and there are some rules. But those rules are not systematic. It doesn't work for all the verbs. It doesn't work for all the nouns. You have to be careful about what word you are using. Okay, and of course, most of the time, when the meaning changes, the word class changes too. That's why we say that it is more involved than the inflectional morphology. And these are some examples. Verbs and adjective to nouns. Okay. So from adjective to noun, verb to noun, verb to noun, verb to noun. Okay. Nouns and verbs to adjectives. We have these kind of, in Turkish we have, in Turkish we have these kind of examples too. Changes from language to language, obviously. But in English they have these stuff. By the way, I can compute, computation, computational, computationalize. I'm just making it up. etc. It can go and go and go, but it is not the same word. It just you are making a new word. So, in an English dictionary, computation and computational are two different words, and they are listed. Okay, so computer, computerized, computerization, computer, computerized, computerizable. It starts with, and it is. You see, it is not that as easy as the inflectional forms. Sometimes, I mean, for all the verbs, do you think that the eyes suffix would work? It doesn't. Okay, for some of them it works. Sometimes some of them is not. Okay, for example, this fixable, it works. Clueable, it doesn't. No such word as clueable. Okay, so irregularity is there. So morphology and finite state automatas, as I said before, we are going to use it to analyze morphologically whatever words we have. Otherwise, you list all the words that is acceptable in a language, and anything other than these words are not acceptable. It doesn't work that way. It is not that easy. Okay, so let's look at this simple rule. Make something plural, regular noun, add an S at the end, it becomes regular plural noun. For the irregulars, I have these direct links. Okay, let's look at these. Fox, foxes, cat, cats, geese, and goose and geese. Okay, these are irregular stuff. The bottom two, irregular stuff here. Top two are regulars. Even with the regulars, we don't write foxes like this, right? This one is not right. It is foxes. I need to insert an E in between. It's a problem with words with ending X and S, right? After these letters, if a word ends with these two letters, you have to put an E before you add this plural S. We need to deal with that. There is a problem with that, and I'm going to. Okay, these are okay, inflection rules, some derivation rules. Let's look at them. It says noun. Let's look at this one. Noun I, verb K, noun L. What do they mean by noun I and noun L? Noun type I. Those are the nouns. Okay, those are the nouns that they can take I-Z-E at the end to become a V. Okay, so this is a noun class. And this is another noun class, noun L, and it can take ative at the end to become an adjective. Okay? Attentive, no. Give me an example of ative at the end. Noun.
It's for the verb I, sir, not for the noun.
Oh, it is, okay, so, sure, yeah. This noun L is here, okay? So verb K, attend, attentive, right? What else? With the go, it doesn't happen, right? Go, goative, no. What, other than attentive, can you give me an example of this attive thing? Compare, comparative, yeah, compare, comparative, right? Yeah, that's good. Yeah. So this is a verb class number K. There are a number of verbs in it, and for these verbs, it works, and it becomes an adjective. For noun type L, if you put a full at the end, okay, joy and joy is not a joy. Yeah, joy is a verb, noun, right? Yeah. joy and joyful, right? It becomes an adjective. So for the inflectional derivational rules, we have this more complicated set. We have this more complicated set. And it looks like, yeah, this is a good question, right? What is the question? How come everything is accepted? Am I not going to reject anything? Am I not going to reject anything? Whatever string I give you, this is going to accept it one way or the other? What's going on? In order to follow one of these transitions, I have to be in noun I set, right? I have to be in one of these words. If I am in that word set, then I am a word, right? Then I am noun I, so it's a valid word. This doesn't say take any character arrays and it is accepted. It says that, okay, noun L is a set of nouns, and these are the nouns. If you are one of them, I accept you. And if I put a full at the end, now you become an adjective. And if you put an nes at the end, now you became a noun again. Okay? So you are starting with a set of known words and verbs. If you are not in one of them, then this one will reject you at this one, Q0. You will not move from Q0. You will stay at Q0. Okay? Of course, I can do a similar stuff for Turkish. And I think I have shown you that one with this paper, with the derivational stuff. Is this a inflectional one? Verbal? Yeah, this is derivational. No, this is inflectional, right? This is inflectional. Maybe derivation will come later. I couldn't find it. Anyways, so similar stuff happens with Turkish too. Okay, good. Parsing and generation versus recognition. What did I say? I can use the finite state machines to recognize a given string. That's one thing. The other thing is I can generate words that are valid in that language only. That's the generation. The third one is the parsing. While I am doing this, I am producing this parsing output. It says that if you are analyzing cats, cat is a noun, and at the end of this word, there is a suffix that represents the plurality. Okay? So this is the parsed version of this one. I found a noun, and it's a plural, right? So I like my finite state machine to produce this output. For that one, I am going to use finite state transducers. Finite state transducers are very similar to finite state machines, okay? The only thing is they say accept, reject, but they also produce, while they are doing it, they also produce this one. Let's go to this example. When I say computerization, okay, computerization, okay. So I started with a computer, so it's a noun. Then I added this noun to verb derivational suffix. Then I added this verb to noun derivational suffix. So it is important to remember where we come from, here to there and there. Okay, I accepted already computerization. I already accepted it. But while I am accepting it, I said I started with a noun, then IZE suffix and Asian suffix, right? I did that too. So that's the parsing of it, like this one. That's the parsing of it. So it is very similar to finite state machine, but it's not accept, reject only machine. It says it's a machine that can that can both say reject, accept. Also the parsing output is there. Okay, so that's the transducer, finite state transducer. Remember, we like to think about the finite state machines like a machine that reads a tape. Now this finite state transducer has another tape. It's an output tape. It will read something from the surface and it will produce this tape, finite state transducer. This is the surface form. Surface form is the form that we read, that we see on the books and on our screens. And the lexical form is the parsed version of it. Parsed version of it. Okay? If I have in the surface form, in my surface form, if I have foxes, okay, remember I put an insert an E for the fox. My lexical form will be exactly like this. Fox plus N plus plural. Okay? It doesn't talk about that E at all. We just ignore it because that's a rule in English that can happen only with some certain letters, certain words only. And with the lexical form, I just ignore it. I don't need to know about it. Okay, so with the morphological analysis, okay, what are we gonna do? We can either use it as a standalone application. Spelling correction is a very important application, right? Or information retrieval. Okay, when I make a search on a database, when I say find me all the information about books, or in Turkish kitap, okay, when I say give me all the sentences that involves this word kitap, okay, when I say this, the system is supposed to return all the words that includes kitab in it, including kitabı, kitabım, kitabıymış, and etc. So you see this one and this one. Okay, so we made these kind of changes in Turkish language depending on our suffixes. So if I say, if my surface form is kitabı, my lexical form should be kitap plus noun plus possessive. Okay, plus first person singular. First person singular possessive. My root is this. So if I do this analysis, and if I am doing the information retrieval, of course I can match the roots now. Because if you like to match this kitab with kitab, those are two different things, right? I need to make this analysis first. Okay. By the way, this is how we represent a finite state transducer. I read a C and output a C. I read an A and output an A. I read a T and I output a T. Okay. Then I output a plus N. I recognize that I read a noun with an epsilon transition without reading anything. When I see an S, I output a PL. PL means plural. Okay, so this is how we are going to update our transitions. What should I output when I read something? And this one is nice, epsilon. Without reading anything, you output a N. Okay, it looks like I am out of time and I couldn't finish this chapter. Next time I will finish this one, and your homework is coming today. Any questions? If there are no questions, then that's it for today. Sorry.